Greetings everyone. So today in this video we are going to do obtain the expression for electric field at an outside point due to a uniformly charged spherical shell. See, we are not going to do only outside, we are going to do both outside as well as inside and on the surface of the sphere. The reason is very simple. This is the one question which has repeated the most of the times in a PU examination for 5 marker. Okay, so according to the previous pattern, this used to be used to say a compulsory question type. So that's the reason we will do this in a more proper way. Okay, and we do all the three cases. So before going to this one, we should have a certain basics. The first and foremost basic is Gauss law. Okay. Gauss law. What Gauss law states? Flux phi is equal to Q divided by epsilon naught. Flux phi is equal to Q divided by epsilon naught. What is phi? Phi is called electric flux. Electric flux is given by integral of vector E dot vector ds, or that can also be written as integral of closed integral E ds cos theta. What is this theta? Say if there are a certain number of field lines are going in a passing through a surface or passing through a space in a space, let us assume that. And I have a certain area, okay, where only few amount of lines are passing through it. So that we call it as flux. Okay, amount of field lines passing through a given area, we call it as flux. The angle between the electric field and the area vector of the plane is theta. Theta is the angle between, okay, the electric field, direction of the electric field and the area vector. So these are the basics required to solve this one. And this is the one of the easiest type of derivation, which we can do very quickly and very easily. If you get this derivation, first give a preference to this one, which can be completed in 3-4 steps, hardly. So since we are doing for a spherical shell, uniformly charged spherical shell, so I have taken a spherical shell and a charge, let us assume that Q on it, okay, and the radius of the shell B, capital R. And now in order to calculate the electric field at a point, okay, we have to draw a Gaussian surface. Okay, we have to draw a Gaussian surface. And here, this is the point P where we are actually supposed to calculate the field. So that is the reason we have drawn a Gaussian surface surrounding it. And the Gaussian surface can be any size and any shape. Only criteria is it should not pass through a discrete charges, and it should not have it should not pass through the discrete charges, and it should enclose the full charges. Okay. And now this is the point where we have to calculate, and we all know that generally for a sphere, the area vector is outward direction. Okay, the area vector is in an outward direction. Therefore, this is an area vector, and the distance from here to P, okay, from this to this is from the Gaussian, from the point of the shell to this point, from the center of the shell to this point is, let us consider it as small r. Okay, this represents the area vector ds, and since it encloses the positive charges, the electric field is outwards. The electric field is outwards. Therefore, from this, we can say now that theta is equal to 0 degrees. Theta is equal to 0 degrees. So let us use, first find the flux. Flux phi is equal to closed integral of vector E dot ds. That is equal to integral of E ds cos theta. Here, since theta is equal to 0 degrees, we can write closed integral of E ds, because cos theta is equal to 1. Cos 0 is equal to 1. Therefore, E into integral of ds. See, this integral of small surface area will give the total surface area. The surface area of a of a sphere is 4 pi into radius square. Now I have to calculate the surface area of this. What is the surface area of this? The radius is r. Therefore, I can say that this is equal to E into 4 pi r square. Fine. But we know that phi is equal to q by epsilon naught. Therefore, q by epsilon naught is equal to E into 4 pi r square. Therefore, E is equal to 1 by 4 pi r square q by epsilon naught. In general, I can write it as E is equal to 1 by 4 pi epsilon naught q by r square. This is similar to the electric field expression for a unit point charge, right? For a point charge also 1 by 4 pi epsilon naught q by r square. So I'll just continue here. You just see. Okay, therefore I can write it in a vector form. Vector E is equal to 1 by 4 pi epsilon naught q divided by r square into r cap, because it changes with the change in the things. Now, just now I took a point here. I was supposed to calculate the electric field at this point. So I have calculated this. If they ask us to calculate the electric field on the surface of the sphere, okay, then also I'll consider this distance as some, what is the distance from here to here? It is r. Therefore, on the surface of shell, E is equal to just a small change, 1 by 4 pi epsilon naught q divided by r square into r cap, position vector cap. Clear? So this gives the electric field due to a spherical shell on its surface. Now we'll see what will be inside it. Let us consider of radius r, and I have drawn a Gaussian inside because here I am calculating the electric field inside the shell. Inside the shell. If you see inside the shell, there is no charge enclosed by the Gaussian surface. That is the formula, right? Flux is equal to charge enclosed by the Gaussian surface divided by epsilon naught. Since no charge is enclosed, therefore this value is 0. Since flux is equal to 0, we know that flux is equal to integral of vector E dot ds. Since flux phi is equal to 0, surface area cannot be equal to 0. Therefore, I can say that E is equal to 0. Therefore, electric field inside a spherical shell is equal to 0. So now it's the time to draw a graph for electric field E versus distance r. See, until and unless it comes to r, there is no electric field. There is no electric field. At r, it will be maximum, and electric field is inversely proportional to position square. It means it is a parabola. Okay, as the distance decreases, okay, electric field increases. In the previous case, okay, in the previous case, we have seen that. Sorry. In the previous case, we have seen that, okay, for a thing, first we have a sphere and we have a Gaussian surrounding it. First, we have calculated somewhere here, and then we came and we calculated at this point. Means as the distance is decreasing, the field increases. Since we have calculated it at r, therefore the field will be maximum at r, and as the time lapses, keeps on decreasing, keeps on decreasing. So it will give a parabolic curve, parabolic curve. I hope you understood the things. Okay. And this is one of the most important derivation. When he asks for 5 marks, you have to write all the 3 cases and a figure. Then only we'll get 5 marks in a PO board. I hope you understood this. Thank you.